Okay guys, we can start. Today I have David Gibson with us with Beyond TAP, polyglot testing with Exeter. A round of applause.
Hello everyone. I'll start by acknowledging the Kaurna people of the Adelaide Plains and also the Ngunnawal and Ngambri people of the Canberra area where I live and work. All right, let's start with some possibly uncontroversial takes. So testing's great. There's a heap of tools for all sorts of languages, all your forges like GitHub and GitLab and so on, have built-in CIs where you can do testing. So we should all be doing it and we don't have any excuses. Well, we'll see. So let's start with a very simple question. How do we write and run a test? And so here's an example in Rust. This is pretty easy. We write ourselves a trivial little function here. I'm just using this as an example. Obviously it's contrived. Just a function that takes a number and triples it. And then to test this further down in the same file, we add a little testing submodule. We mark a function as a test, and it just asserts that 222 is 6. Simple enough. You run cargo test to test it. It runs a test, it passes, hooray. Or maybe you prefer Go. Pretty similar deal here. Here we've got a version of that function in Go. And now in Go you put the test in a separate file called _test, but otherwise it's fairly simple, fairly similar. You do have to import this testing module, and you write again a test function. It checks if 222 is 6, and if not, it fails the test with this call to the error function. You run go test to run it, runs a test, passes. All right. But what if you're not using one of these cool newfangled languages with built-in testing stuff? Let's have a look at this in Python. In Python, we have our same function again, and Python has a unit test module built into the standard library for doing this sort of thing. And so you import unit test module here, it's in the same file again. You define a class, which is a descendant of this unit test case class. It's got a test method that again does an assert that 3 times 2 is 6. And you can run that by invoking the unit test module and pointing at your thing, and it runs a test. Now, if you're familiar with Python, you might start to notice a couple of little oddities here, though. One is, so this is a method call, this self.assert equal, but the convention in Python is that method calls, or method should be named in snake case, and this is in camel case, but this is in the standard library. And the other thing you might wonder is, what is this class all about? What does an instance of test triple represent? Because we're not putting any data into that instance, and we're not taking any data out of that instance, so what's it for? Why is it not a function? And that's what I just said. And the reason is because Java. So we need to talk about JUnit a bit. JUnit is the de facto standard unit testing framework for Java, and it was one of the earlier frameworks that became very popular, and because of that it was enormously influential. So it helped popularise testing widely, yay, I guess, and it inspired a lot of similar frameworks, which are often called XUnit in various other languages. The bit that's not so good is that lots of those things pretty much exactly copied the interfaces of JUnit, even the bits that don't really make sense in a language other than Java. Now, admittedly, in this example here, that's kind of trivial. Okay, the capitalization's a bit weird, and there's class that doesn't mean anything. So that's the fact that the Java convention is to use camel case for methods, and Java has no way of grouping functions together other than classes, so there's a class. There are more serious problems that I don't really have a lot to get into, but in particular the JUnit, at least the basic parts of JUnit, make it really hard if you want to mix and match different fixtures with different tests. It's possible, of course, but it's pretty awkward. So that Java influence is not necessarily a great thing when it shows up in other languages. There is an alternative in Python. There's a pretty popular tool called PyTest. It's not part of the standard library. It does a heap of things, in fact, but one of those things is it lets you do this test more simply, just as a straight function, and you can invoke PyTest, runs the test in much the same way. All right, now let's get hard. Let's try and do this in C. So we can write our function easily enough, and we can write a function that tests it. We've put it in the same file here. So we have this test triple function, and it asserts that triple 2 is 6, and so that assert will just blow up if it's not true, and otherwise it'll pass through and nothing will happen. And we run this somehow. Now, obviously there are ways to do this, and we'll be looking at some a bit later on, but there's not really an obvious choice for C. There's a bunch of frameworks you could, none of them are sort of popular enough that they're a de facto standard or even an obvious first choice for how you do this. So that's another wart in the sort of current testing environment. All right, let's ask a slightly harder question. How do we write and run a bunch of tests? So let's go back to our very first test, this one in Rust. We're only testing one case, which is a bit poor, even for something like this. Testing 0, testing negative numbers would probably make sense for this function. They're the sorts of things that, for anything more complex than this, you could easily get wrong and, be good to test them. So obviously you can write a test just like this. You write one function and then you check that 2 times 3 is 6, and 0 times 3 is 0, and minus 3 times 3 is minus 9. And you can run it, but it shows up as one test, which, again, with this trivial contrived example, maybe not a big deal, but really, when you've got things, you're really testing 3 separate things here, you'd like them to show up as 3 separate tests, so that you can quickly see what case has gone wrong. If you need to debug it, you can run just that test and debug what's going wrong there, and then when you think you fixed it, you can rerun just that test and quickly check if you have actually fixed it before you rerun a whole test suite. So if we want this to show up as separate tests, there's several ways we can do it, but one way we can do it is this. So here we have test triple. So that's a function, but it's no longer technically a test in the Rust sense. So it takes parameters now. It takes the number you're tripling and what we expect the answer to be. And then we have separate test cases. So we've got 3 here, which invokes that function with different parameters. So we test those 3 cases we were talking about. And now when we run it, we get the 3 separate results as 3 separate results as we're aiming for. Great. Let's make it a bit harder. What if we don't want to just test a fixed set of cases? What if we want to test every case in a whole loop? We want to generate a bunch of cases from our code. We could do it like this. We've got this same parameterized test here, and we have a test case here that runs through every number from -3 to 3, and it tests that multiplying n by 3 is the same as adding itself to itself. Again, contrived example, but you get the idea. So we're trying to do that, but of course now we're back to running, for this showing up as a single test. We don't get each of those cases as a separate case, so that's a pity. So this is what's called a parameterized test. So it's a test which takes parameters, but specifically I'm talking about tests where the changing the parameters represents different cases that you're testing, as opposed to parameters representing environment that you need to just run the test in the first place. And there's a few cases where that's useful. One common one is table-driven testing. So that's where you have a bunch of specific cases you test where you've got the inputs and the expected output, and it's easier to write a table of those than to write that out every time. You just want to step through the table, run all of those. Often you might have a complex function and you're testing one particular aspect of its behavior, and for that particular aspect, this parameter doesn't matter or shouldn't matter. And you want to test all the possible values of that parameter and make sure that you get the same answers. All these things should behave the same. Let's check that they actually do behave the same. And the other places this is useful is property testing, which is a thing that somewhat comes from the functional programming world. And that's kind of what we're doing with that n plus n plus n. So there's some mathematical property of your function that you can test more easily than just re-implementing your function. So an example of that might be if you're testing a sort function, the answer should be sorted. Doesn't matter what the input is, the output should always be sorted, and you can check that fairly straightforwardly. So parameterized tests are useful, and that leads to what's called a test matrix, where you want to run a parameterized test across a whole bunch of inputs. So the name comes from if you've got several parameters, you know, you're testing all the values of this and all the values of that, and so you can sort of have a table or matrix of all your possible combinations of results. All the examples I'm going to use here are just a single parameter, just to keep things simple. But that's a test matrix. And we'd like for these to still be separate cases in the runner. Like I said, so it's quicker to rerun a specific test if it's failing. It's less extra noise when you're debugging, extra traces and so forth. And so what do we have in the way of support for this? So Rust, you can't do this. I mean, there's probably some crate that does it. You can probably do it by futzing with the test runner bits in C, but in the basic Rust testing, what it provides, no way to do that. That's a pity. Go sort of does. It has a thing called subtests, but that only reports failures differently, not successes, which is a little bit weird. You can do this in Python unit test, although it's kind of just abusing the fact that Python is such a dynamic language. So what we're actually doing here is we're making one of these test classes with nothing in it, with no actual test. And then we do our loop. We create an instance of this test function for a particular value, and we poke that function into the class as a method. So it's really using Python's dynamic introspection stuff to kind of modify what's going on. It works. We get all these different cases as separate things, but it is a bit awkward and a bit arcane. PyTest does have a nicer way of doing this. You can add this decorator to a function saying basically run this test across these parameters, and it'll do the same thing. All right, another question to ask is what should we be testing? So all the tests we've looked at so far are unit tests, and they're testing basically one internal function. Now that can certainly be useful, but a good test, like a good comment, should test what the code does, not how it does it. And if you don't do that, what tends to happen is you get a test that needs to be changed every single time you change the code. And that is unfortunately quite common in projects which have mandated adding unit tests for every new function you add, which is not great. What's really more important than testing the unit tests of this limited scope at least is testing the external interfaces of your project or module. That's, after all, what users actually care about. But equally important, those change less, which means it's much easier to maintain your tests. So this is called integration testing, except integration testing is also sometimes used to mean larger scale integration of complex modules. It's sometimes conflated with unit testing, and it often uses some of the same tools. I'm going to call this interface testing just to be specific here. I don't think that's a particularly standard term, but that's what I'm talking about. All right, so how would we do this? Rust has specific support for this. Rust does call them integration tests. This is very similar to our previous example, except now our test, instead of living right next to the code that we're testing, lives in this separate tests directory, which is for integration tests. It's now a public function rather than a private function, and we have to explicitly import that function into the test code because it can only, the test code now only has access to the actual exposed interfaces of our library. Other than that, all the logic's the same. We run them, and this is running so the first bit here, zero tests, is the unit tests, the internal ones, which this example doesn't have any of. Then it's running the integration tests, so one test, the one here. All right, straightforward enough. You can do much the same. Well, there's not explicit support for it in Go and Python, but you can basically do something similar just by putting your tests in a separate module from the code you're testing. Let's look back at C. We can make the public function. We can write a thing that includes the header, does the test. Still no real obvious way to run it. Still a bit of a what. Now, not everything's a library, of course, but everything does have some kind of interface. It could be a command line interface. All your configuration files are effectively interfaces. Any data files you read in or you write out is another interface. Any network protocols you speak is an interface, and HTTP APIs are obviously a common example of that that's very important these days. It could be a full-blown GUI. All of those introduce their own complications. I'm not going to get into much of that except to note that it is something you have to do. Let's have a look at command line interfaces though, because that's about the simplest example of an interface. It's not like a library interface. So here's a version in Rust. So now our triple thing, rather than being a function in a library, it's actually a program that, so it takes the command line arguments, it takes the first one. Every time you see unwrap, that's just trivial error handling, just blow up on any errors. We take that string of the command line argument, we parse it into an integer, throw away errors, and then we print out that number times 3. So this is a tiny command line program, takes an argument, triples it, prints it out. Okay? So Rust integration tests can also be used for testing binaries in this way. And Rust even, or Cargo specifically, provides this end thing. So this is a way you can get the path to the binary you've just built, specifically in order that you can test it. So we're using this Rust std process command. That's the Rust standard library way of running external commands. So we're saying we want to run an external command of the binary we're testing. We pass it the argument 2. We run it and we get the output, handle errors. We take that output, which is bytes, and we turn it into a string, assuming UTF-8. That's just Rust being pedantic. We trim off the new line that's on there. We parse it into an integer, and we check that that integer has the value we expect, 6, 3 times 2. So it's more complicated, but you know the concept's basically the same. You can do that. You can do the same thing in Go or in Python. I don't have examples for those, but you can do basically similar things. Okay, let's tackle this one in the C. We can still write our program pretty easily. Take the first command line argument, turn it into an integer, print it out times 3, exit. Now, you'll see I've had to reduce the font size here, which kind of gives you an idea. This is kind of awkward, and this is actually even dodgier than the previous example I gave in Rust in terms of cutting corners and being sloppy about all our edge cases. We still don't have an obvious way to run this, and testing a CLI in C just kind of sucks. Okay. So far in all the examples we've looked at, the test runner has basically come as part of the language we're testing, and that has required that we write our tests in the same language that the code we are testing is in. But as we've just seen in C, it might be easier to write our tests in a different language than the original code we're testing. Or even if that's not the case, you might have a project with multiple languages involved in it for whatever reason, and you don't want to run separate tests for every language because that's awkward and doesn't give you collated results and blah, blah, blah. So that brings us to language-independent test frameworks. Now, I'm going to talk about a couple here, Bats and Avocado, not particularly because they're the most well-known or the best, but because they illustrate points I have. There are heaps of these, including any number of extremely elaborate, enterprisey, proprietary ones. There's heaps of these. I'm just going to scratch the surface of this. BATS first is the Bash Automated Test System, and as you might guess from the name, it's a really simple framework that is written in Bash, and you write your tests in Bash as well with small annotations. So what does that look like? Well, we can finally test our little C program here. So here we have our C program. This is the command line version that takes a number and triples it. We can write a BATS test for this. So you say this is run with BATS. The at test, so this is the special syntax that BATS understands. You say this is a test, this is the name of the test, 222 is 6, and then you just have a command, and anything that fails in here means the test fails. So this is just a shell command, so we run 222, we get the output, is it equal to 6? All right, we can run BATS, we get a test, it passes. Hooray, we finally tested our C program. So BATS, you can test any Unix program with a CLI this way. Great. It's really easy to get started, so that's great. And shell, of course, is really good for testing command line interfaces because the entire point of a shell is running command line interfaces. On the other hand, shell is kind of terrible if you want to do anything complex. Especially if you need data structures in your test itself to keep track of what you're doing, it's a real mess. My colleague on my other project will probably complain about that because he really loves shell, but I think that's the case. Tracing, if you want to debug this thing, can also be really confusing because you've got lots and lots of short-lived processes that the shell is invoking both within what BATS is doing itself and within your test potentially. So if you do like an strace of this, you could have dozens, hundreds of programs, each with their own startup and just a lot of confusing things going on that makes it hard to figure out where things are actually going wrong. And BATS has no support for test matrices. That's a pity. The other one I'm going to talk about is Avocado. So Avocado is a very featureful framework. It's open source, of course. But it is largely developed and used in Red Hat. I don't know of many people using it outside. It has a bunch of ways of writing tests, which it calls test types. The kind of primary one is what it calls Avocado instrumented. So these are written in Python. They're essentially an extended version of the unit test test case stuff. It has some other types, some of which we'll cover a bit later. So what does this look like? So here is an Avocado instrumented test written in Python. So we import Avocado. We're importing another helper function from Avocado here. We have our test class, just like unit test, except now it descends from avocado.test instead of unit test. We have our test function. So this get output function, that's a helper provided by Avocado that basically runs this command line, 222, and gets the output, puts it into this string. So we're testing exactly the same command line program as we test in the BATS example just before. And then we check that the example, so we get the output, we turn it into an integer, we check that it gives the answer we expect. And we can run with this with Avocado, and it starts it up, it runs it, it passes. Hooray. So Avocado has a heap of formatting and collation options, which can be useful, particularly if you're doing extensive sort of serious stuff. It records all your previous test results by default, which can be great if you later want to go back and sort of do statistical analysis of, what tended to fail and blah, blah, blah. And Python's a pretty versatile language. Avocado provides a bunch of helpers, which can be useful for doing that. And Avocado does support test matrices, which it calls varianting. Avocado is not particularly widely known, outside of Red Hat at least. It's a pretty complex framework, which again means when you're trying to debug a single test, the traces can be really, can have a lot of noise in them from the framework before you get to what you actually care about. It kind of has this Java poisoning problem like unit test, where the interface is copied from JUnit, which is not great in Python. And the varianting, although the support is there and it can do some very cool things, it is really arcane to use to the point that I'm not going to give you any examples because I barely figured it out myself. All right. So we've now separated the language we're testing from the language we're writing the tests themselves in. But the test runner we're using still is kind of selecting the test language for us. So Avocado was, or Bats was picking Shell for us, Avocado was picking Python for us. But we might have some tests that are easy in Shell, but other tests that are not easy in Shell, and you want to use something else. Even without that, you could have a bunch of pre-existing tests that are written in different languages, and you want to run them all together. So it'd be nice if we could also separate the language we write our tests in from the test runner we're using. And the way this is usually done, is what's called a test protocol. So this is a standardized way for a test runner to invoke a test and get the result back. So it separates running the tests themselves from discovering the tests, so figuring out what tests are run, scheduling and running them, and reporting them. There are several of these, not nearly as many as there are frameworks. I'm going to talk about two. The other big one is XUnit XML. I'm not going to talk about that, although it is used a bit. These are kind of the three ones that you see a lot. Exit code protocol, this is so simple and so widespread that people don't really think of it as a test protocol. This is basically every test is an executable command. You run it. If it exits with status 0, it's a pass, otherwise it's a failure. Sometimes there are some extensions. So example here, now we have our C library example, and we can write our test as a C program with a main function here. So we assert, and then we exit. So if this is correct, the assert will do nothing, it'll exit with 0, that's a pass. If it's not, the assert will blow up, that's not an exit with 0, that's a failure. We can run those. Avocado can run these as well. I said it had several test types. This is the exec test type. So here we can run that, and we have the output. You can also run with them with Meson. This is quite important because Meson's gaining popularity as a build system, and doing your tests in there as well is nice. So here we need to we tell it how to build our test executable, and we tell it to run that as a test. Basically the same idea. Meson runs them. So exit code protocol almost universally supported. Meson and Avocado do it as we see. And if you've ever hand-rolled a test runner, chances are this is how it works, basically calling things in this mode. It's very easy to debug a single test. You just run it directly without the runner, and you get almost no noise. One executable per test is real messy though, and there's basically two ways you can do test discovery. Either you can have a separate list or a script saying what tests to run. You have to keep that up to date. That's sometimes a pain. Or you have a big directory of all the executables you want to run as tests, but then you can have a build error that just means an executable is missing, and instead of a test failing, you just get the test vanishes. So that's not ideal. The other one that's very common is the test anything protocol. This came from the Perl world, and it's basically just this text output. Starts with a version, what they call the test plan, which tells you how many tests are running, and then you get either OK or not OK for every test case, which is they're called test points in TAP terminology. So an example of that, we haven't used Go for a while. Here's the Go version. So this is so we've got a Go function here, and we're using this library to do tap output from Go, and we're testing multiple things to show how that works. So we have this function that takes, again, the input and the expected output, and this t.ok generates either an OK or a not OK, depending on this Boolean parameter. So if the answer is right, it generates an OK. If the answer is wrong, it generates a not OK. and this is the test description or name that goes on the test point. Here we run it on our 3 examples. You can run this manually and you can just look at the tap output. There it is. Or you can run it in a runner that understands tap. Prove is the classic one from the Perl world, and it runs all the things. There you go. Tap is easy to generate, it's easy to parse. Lots of things produce it, as well as there being libraries for basically every language. There are other test runners that can generate tap output, so Avocado and Mason can both do that. A lot of things can consume it and report on it, so prove is the classic Perl one. Mason can do it. Avocado can sort of do it, although it's got some limitations. And you can write your matrices directly in your test language, so nothing new to learn. Hooray. It is showing its age a bit. The tests have numbers and descriptions, but not a sort of ID. And if you insert new tests in there, the numbers will change. Descriptions aren't always stable. There's nothing guaranteeing that the description is identical if the test fails or passes, which is a bit ugly. And you're usually running a bunch of tests from a single binary. So you can't run a single test point on its own. You've got poor isolation between the tests. All the other tests provide noise for when you're debugging one of them. And they run in sequence. That's not strictly true. There are ways of running them in parallel. The recent versions allow you to do that, but the libraries still tend to encourage you to run them sequentially. All right. So what we'd really like is to be able to write tests for any language, in any language. We'd like to be able to write multiple tests in a single source file, just because that's convenient, but still have their results reported separately and allow the list of tests to be discovered. We'd like to be able to run the same tests from multiple runners. We want to be able to run each test on their own with minimal overhead for debugging and logging. And we'd like test matrices, preferably with constructs that are natural in the language you're writing the tests in, so you don't have to learn a whole other system for doing that. And without sacrificing being able to run each test separately. So Exeter is my attempt to do this. It is basically 2 things. So it's a test protocol, which is an almost trivial extension of the exit code protocol. Your test program takes an argument, either it's --list, which prints out all the tests the program can do, or you give it one of those IDs that came from list and it runs just that test. And then it's a set of little libraries, so far in Shell, Python and C, that allow a program to easily produce that test protocol. It's trying to be idiomatic in each language it's in, and that's considered more important than having entirely identical interfaces in the different languages. Some trivia there. It's not trying to run or schedule multiple tests. That's left to some other runner. It's not trying to format results in any meaningful way. So an example, here's a shell one. Here's our little command line thing in Rust again. And here's how you'd write an exeter test for it. So you source this exeter.sh. This is basically the closest you can get to an import of library in shell. This is just a variable with the binary we're testing. And you say exeter register for each test. So you give it a name. So this is a test that's correct. So 222 is 6. So this is just a shell command. And here we've got a test that's wrong to show what happens when you fail. 222 is 99. And then at the end, you invoke exeter main with your command line arguments, and it will do that exeter interface I just talked about. So you can invoke this manually if you really want. So you can get the list. There's 2 tests, right and wrong. You can run the right test. It passes, exited with 0. You can run the wrong test. It fails. These are so simple that there's no diagnostic. You can print out anything you want as diagnostics, but you don't have to. Obviously, that's a pretty awkward way to run things. Right. The easiest way to run them at the moment, nicely, is with Avocado. This does have to be a pretty recent version. With this rather awkward command line, Exeter will actually, Avocado will talk to the thing, get the list, run all the tests. So here we're just pointing it at this with these complicated arguments. Runs the 2 tests, one of them passes, one of them fails. Here's an example of a test matrix. Basically the same thing, except we have a loop, and inside the loop we do an exeter register. There's the answer, the results. Python, very much the same thing. We define a function with our test. We register the test. We run exeter main. The Python module has some niceties in it. The Python's the most developed one at present. Instead of explicitly registering, you can use this decorator to automatically register things. And again, a test matrix. So this exeter register, at least the Python version, as well as the function, also gives it parameters. So here we can just do a loop, and we give both the function and the parameters, and it will run that function with those parameters as one of the test cases. And we're just generating a name for it here. No handy decorator for that yet. C, much the same thing, register and run. There are some limitations here because C doesn't have closures or lambdas. This is a bit awkward, so you can't pass the parameters in now. I hope to find a way to improve that, but it's not so great at the moment. I'd like to be able to run them from Maison. You can ask me about this later. This almost works, but not quite. Because exeter tests are exit code tests, you can run them up to a point with anything that does that, which is nearly anything. And sometimes you can use a script to run -- list and turn that into the config you need for whatever runner you've got. It's pretty easy to incorporate into a hand-rolled runner. Here is a basically trivial example of that just runs through all your tests. I'm going to skip that one. This is in really early development, basically. I hoped when I wrote the abstract that I would have more done by this stage. Of course, that didn't happen. There's a lot to do on this. I'd like it to be nice to run tests with Maison. I'd like to be able to do parameterized tests in C. I'd like to be able to take the output from one of these things and turn it into tap for all those runners that do handle tap already. It'd be nice to have some real-world users. This is done in order to test for the past project as my main project, and I've started, but we haven't really got there yet. More languages, more runners, and some kind of test metadata, in particular telling the runner how long its timeout should be before you just kill the thing off would be nice to have. Like I said, this is really early days. Nothing is stable. If this sounds useful to you, please talk to me and let's see if we can make this thing a bit better. And we are at the end. The tests are actually on GitLab, but I do not have a link for them there, sorry. All right, I'm done.
Okay, we can have about 2 questions.
Okay.
Any questions? We can fit 2. No? Then a round of applause? Oh, no.
Sorry, just one. This might be a bit too detailed, but when you ran your test with -- list and then did for ID, I was just wondering, does each test registered have a stable ID?
That's the intention. I mean, obviously, you could mess that up if you wrote your thing to not have stable IDs, but the intention is that you have stable IDs and you name the tests that way, yeah.
I mean, if, like, say I add a test, you know, in the middle or at the end or whatever, do the other ones?
Yeah, no, that won't mess with the IDs unless you go out of your way to make it mess with the IDs. Yeah.
Okay, on my way.
Slightly diverting question. I just read the README about the naming. You from Tassie originally?
Depends what you call originally. I lived in Tasmania from when I was about 10 until the end of high school, and my parents still live there. So yes, it's named. He's referring to the fact that on the GitLab site for Exeter, it points out that this is named after Exeter, Tasmania, not Exeter, England, or any other Exeter, or executable tester, of course, which is what it officially stands for. All right. Well, that's all we have time for. Please feel free to talk to me.
Round of applause.